Now, we're going to go with the graph for the action potential. And so what I want you to recognize is that it's at a negative 70 millivolts for the resting membrane potential. This, when you go to touch your finger, it's got to get it to the threshold, minus or a negative 55. And then if it gets there, it's going to go all the way. And so it'll go to the positive 30, which we're going to see as depolarization. What I'm going to do is just draw the graph on. You can use yours as well, but let me put this on right now. From the stimulus, it's going to go up, it'll peak, and now as we look at this, let's put what's happening as this is going. Sodium is going into the cell. That's what's happening here. And so I'm just going to write this right here. So for this to go up to a positive 30, sodium has to go into the cell. And as it does, it goes up to the positive 30, and then what's happening here? Because this was called depolarization. So if you'll just put a note here. So depolarization, it's changed from the negative to the positive. It's changed the polarity, and now this is what it is at the positive 30. What then happens is potassium leaks out. And as potassium leaks out, then it's restoring it down to this. And so as the positive potassium goes out, it makes the outside positive again, and this goes back to negative. And so I'm going to put this here. So the positive is now going out of the cell. It's the potassium that's going out, and it is making this positive again outside. It actually overshoots. It goes past negative 70, and that's called hyperpolarization. So as extra potassium goes out, it goes below the negative 70, and here we've got the hyperpolarization. But then it's got to have it so that the potassium has gone out, the sodium has gone in, but it needs to restore it so that sodium is outside, potassium is back inside. And that's where the sodium-potassium pump comes into play. And so as we look at this area right here, the sodium-potassium pump is going to restore the natural balance. And so I'm just going to put a note here. That the sodium-potassium pump will be used. And of course, it brings it back to what we see here, the resting membrane potential. So this is the situation that we've got with an action potential for the neuron. And obviously, it was positive outside until you get sufficient stimulus that forces the sodium goes in. As the sodium goes in, it changes this from positive to negative, and then we get the potassium leaking out, changes this back to positive outside and negative inside. It overshoots it, that's the hyperpolarization, but then we get the sodium-potassium pump. What's it doing? It's actually making it so that sodium goes outside, potassium goes back inside, and it's ready to fire again. And that's the action potential. And so we've got the charges that we have here. What would happen if it took more stimulus to actually make this occur? And so that if it took more stimulus, if it would have to reach up to here before it started, and so that would be a problem. If it was going to have their threshold down closer to the negative 70, it would make it so that it would start even quicker. It wouldn't take as much stimulus. And so those are some things that can happen with the threshold as well. Now, we've got the threshold done. What I want to do now is just to go over to the next page and let's look at this. For this one, we've got the neurotransmitters. Neurotransmitters, the first one that was identified was acetylcholine, and it's always at a neuromuscular junction. Norepinephrine, as you can see, it's going to be a stimulant, especially for the heart muscle. And the other thing is it gets us up in the morning. It arouses us from deep sleep. So epinephrine that we've got, another name for it, adrenaline. And then the next that you've got is dopamine. Now dopamine is deficient in Parkinson's. And with Parkinson's then, they're going to have that shuffling gait. Their body doesn't have the dopamine to stop the action. And so the other thing is the pill rolling, the hands going like this. And sometimes the person will actually, if they got Parkinson's, reach out to stop themselves. So if they're shuffling, then they'll reach out and that can help them stop. So dopamine is the one that's deficient in Parkinson's. The next that we've got is serotonin. Serotonin, with Prozac for an antidepressant, it actually makes it so that it lets the serotonin stay there longer, and it doesn't let the serotonin be taken up. And in that way, it makes them feel good longer. And so serotonin very much in place with the antidepressants. The next one, endorphins. Now for endorphins, I'm just going to put this word here. Now as you look at this, you can see the endo. Endo means inside. But I want you to look at this part, and this is from this. So what are endorphins? It's like having morphine inside us. It's a painkiller. If you have run for 40 minutes, you get endorphins, and they'll call it a natural high because you get the endorphins and it makes you feel good, it cuts down on the pain, and so this is what you'll see. Endorphins then, when they found these, the endorphins in the body, they realized there was this receptor for morphine, and they started looking for these, and then they found endorphins, and that's what we see. Now, for endorphins as well, then this is an important thing with acupuncture. As they do acupuncture and it makes the pain, it also releases endorphins. Another thing that they'll say is laughter. Laughter actually releases endorphins. And that's why they'll say if somebody's in a lot of pain, maybe help them watch something that's a funny movie, because it releases endorphins and helps to shut down the pain. So we've got the endorphins. Now I want you to look at glutamate. For glutamate, would you underline where it says it's a stroke neurotransmitter? It excites the neurons to death. And so with a stroke situation, there's ischemia that's happening, decreased blood flow, and glutamate is going to just excite these neurons to death, as we see. Now, that gets us through that page on 72, and I want to go over to the cross-section of the spinal cord. And so as you look at this for the cross-section of the spinal cord, I'll just draw one quickly, and we'll go over that right now. Okay, let's start to work on the spinal cord. First of all, there's dorsal, there's ventral. Where's the gray matter? Here's gray, here's white. What is white matter? It's myelinated. What's the central canal? Now, where you've got central canal, it's number 5, and where you've got that, would you put has ependymal cells? And so here I'll include this. So ependymal cells are lining the central canal, They have cilia, they sweep the CSF, move it along, and so we've got this right here. Where are the different horns of the gray matter? Here's dorsal horn, here's ventral horn, here's lateral horn. So we can see those. Also, I want you to recognize the dorsal root ganglion. Now the dorsal root ganglion will have the sensory nerve cell body, and often you'll see this mnemonic. What does it mean? This is sensory, afferent, dorsal. Now, as we look at this, I'm going to put in a sensory neuron, and so here, we just enlarge that a bit right there. So we've got this one coming in. And on your diagram that you've got, this is going to be a withdrawal reflex. A withdrawal reflex is going to have an interneuron. And so just down over here, I'm going to put the little diagram that just shows there's like a pin or tack that has been affected. And here's the pin. Okay, so for this one, I'm going to connect the sensory right over to here. And so we change this and we'll get it going. If you put an arrow, sensory is going in, it's afferent. It's going to come in dorsal root ganglion into the dorsal area. And then I'm going to put just a green interneuron. And so here we've got it right here. Of course, interneurons are in the gray matter. There's not myelination on them. And I'm going to put here now, as you see, this motor neuron is efferent. Efferent, it's coming out to the muscle that's right there, and I'll just include some muscle cells, and we've got these, and it's coming to them. Withdrawal reflex, it will have an interneuron, and so we're going to have sensory. Interneuron sends another interneuron to the brain, lets you know that it was your hand, it hurt, and it also gives a response. So this is going to have other interneurons. For the rest of this, I want you to put on here, and I'm going to use blue for this one, and right here, and this one I've got labeled as number 6. And so here we've got number 6. Number 6, when we look at corticospinal tract, cortical means it's coming from the cortex to the spinal cord out to the arms and legs. This is efferent, it's motor, it's going out, and so corticospinal, it's a tract, it's in the myelinated fibers here, and so we've got that one. If you'll just put another one just down in here, and this one is going to be the spinothalamic. Where is it coming? It would be the sensation. And sensation from the arms, the hands, the legs, it's coming to the spinal cord, to the thalamus, and it's relayed on to the parietal lobe where it's identified that it was your hand or your toes. And so then spinothalamic is going to be afferent, it's like this one, and it's going to go for sensation. So this one is sensory. This one is motor, and we've got those. Now, I want to also put up the stretch reflex over on this side. Now, the stretch reflex is a spinal reflex. It's not sending a message to the brain. it's sending it right through the spinal cord, and it would be like the knee-jerk reflex. If you were to do the patellar hammer test, then it would actually hit your patellar tendon, it would make the quadriceps fire, and it would try to extend your leg. That's what that would be doing. So let's look at this one. And over here you've got a picture just of the leg. I'm just going to put one here. And there's the foot, there's the leg. There we go. Okay, so now that we've got the leg, what is going to happen? As that little hammer, and so here's that hammer that they're going to use, I want you to see where it's sending the message. And so from here, there's going to be sensory. I need to put on dorsal root ganglion here, so let me get that up. And as we look, here is a sensory neuron. And there's its cell body. And for this one, it's just one synapse. So it's called monosynaptic. As you look here, here is the motor. It's going out. It's one synapse, so it's monosynaptic. It's the same side, so it's called ipsilateral. This one's same side, but it's got more. It's polysynaptic, and it's ipsilateral. So we've got those for the reflexes as well. Now, I do want you to just draw the dura mater. And so I'm going to put it around here. And so the dura mater is around the spinal cord. And this has to do with epidural anesthetic or a spinal anesthetic. And so on yours, if you can just put an arrow, and I'm going to use just a red coming through here, and that would be a spinal anesthetic. What is it doing? It's going through the dura mater. It's putting the anesthetic into the CSF. It's going to be a really quick response within like 5 minutes. But what is an epidural? And so I'm going to put another arrow, and for this one, I want you to see here, and this one, I'll just have it come out here. And this one, outside the dura, epidural